All right, folks, in this last section in Chapter 10, Section 10.8, your book calls it Choosing a Convergence Test. I say it's also known as a cumulative review. And you know what? We've learned a lot so far in this chapter. We've learned many tests for determining if a series converges or diverges. Also, as we've been going through each section, I've been kind of telling you, like how I think I originally called it cataloging series, but I said you have to start to recognize things to see how you're going to attack the series. So I've been all along kind of foreshadowing, what the book is calling, this section 10.8. In this section, the book's going to discuss a general strategy. But again, that's something we've been discussing all along in each and every section. Again, I think recognition is the key. Now, in your book on page 701, table 10.4, it contains everything we have learned in this chapter about series. And here's what it looks like. It's a big table. And let's see, there's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different things listed here that we've learned. The one thing that isn't listed in this table, which I don't know why, is telescoping series. But this is everything that we've learned. I would point out, we've learned all of this throughout the chapter on a section by section basis. There's not much more to say other than, remember, the book calls it the divergence test. And I say the better name for it is the nth term test for divergence. The book has a comment here is, it cannot be used to prove convergence. We know that, and that's why we call it the nth term test for divergence. But that's just like a summary of everything that we've done in this chapter. And folks, there is absolutely nothing new in this section. It's just a collection of exercises where anything is fair game. Anything that we've studied so far in Chapter 10 is fair game. Because there is nothing new here, all I'm going to do is I'm just going to work out some of the exercises in the rest of this video, share with you what I'm seeing, why I'm seeing what I see, and how to attack the series. So the section 10.8 exercises that I'm going to do in this video are numbers 17, 19, 25, 27, 49, 53, 59, and 69. And as always, I'm going to suggest that you try them before watching my video solution. Who knows, maybe I'll give you a hint before you try it. Maybe not. So in any event, I'm heading off to the board to do number 17. You try it first. So as a hint for number 17, think about why when I look at 17, I'm thinking nth term test. So pause the video, try number 17, then restart the video, and I'll be at the board working it out. All right, number 17, we're asked, is the series n equals 1 to infinity, quantity negative n cubed over 3n cubed plus 2, does it converge or does it diverge? Well, here's the first thing that I'm seeing. Inside parentheses, it's a negative n. That's really negative 1 times n. So there's a rule of exponents that would allow me to rewrite this as a negative 1 cubed n cubed over 3n cubed plus 2. But notice this is the exact same thing. Negative 1 cubed is negative 1. So it's the same thing as this. And now when I'm looking at it, I'm thinking, the nth term test. When I'm looking at this limit, as n goes to infinity, negative n cubed over 3n cubed plus 2, I divide everything in the numerator and the denominator by n cubed. I get a negative 1 over 3 plus a 2 over n cubed. That limit is negative 1/3, which does not equal 0. So, our conclusion, the series diverges thanks to the nth term test for divergence. So that was 17. Number 19. Give you a little hint for 19. I look at it, I'm seeing rules of exponent may help me rewrite it so it looks like something that I know. So pause the video and go work number 19, and then after you do number 19, restart the video. I'll be here working it out. Alright, number 19. Does the series n equals 0 to infinity 3 to the n plus 4 over 5 to the n minus 2, does it converge or diverge? So when I look at it, the first thing that pops into my head is, well, if it were just 3 to the n over 5 to the n, it's a geometric series. And I can get there by using rules of exponents. 3 to the n plus 4, well, that's 3 to the n times 3 to the 4th. 5 to the n minus 2, well, that's 5 to the n times 5 to the negative 2nd. Then I can bring 5 to the negative 2nd upstairs to make the exponent positive. So that gives me 3 to the 4th times 5 to the negative 2nd times 3 to the n over 5 to the n. And then pulling it up here, that's a positive 2. Pull it upstairs, the exponent becomes positive. I think 3 to the 4th times 5 squared, see that's 81 times 25. I think that's 2025. And we have another rule of exponents here, 3 to the n over 5 to the n. I can rewrite it as 3/5 to the n. So yes, this is a geometric series. The original series was a geometric series. It's a geometric series. R is 3/5, which is less than 1. Therefore, the series converges because it's a geometric series. And even though we weren't asked to classify, I could classify this as being absolutely convergent because the geometric series has built into it absolute convergence. But that was number 19. So next up, I'd like you to do number 25. Now let's see, a hint for 25. I don't know. I look at that and I'm thinking integration might be very helpful. So pause the video, try number 25. When you're done with it, restart the video. I'll be here working out the solution. Alright, 25. Does the series n equals 1 to infinity 1 over square root n times e to the square root n? Does that series converge or diverge? And then I said, I gave us a hint, it looks like integration might be helpful. So what jumped out at me was that if I had the function 1 over square root x e to the square root x, to me that's something that I can easily integrate. I'm kind of looking ahead. If I were to integrate that, I'd let u equal square root x. Then du is 1 over 2 square root x. So I think it's easy to integrate. And let's continue. First thing I would check that function, and it is positive, continuous, and decreasing in the interval 1 to infinity. So I'm kind of looking at the preamble of the integral test now. So why don't we go ahead and evaluate this improper integral? Which we know to rewrite this as the limit as b goes to infinity, the integral 1 to b, 1 over square root x e to the square root x dx. And like I just kind of foreshadowed, there's a u sub here. U is square root x, du is 1 over 2 square root x dx. So this integral, when I crank it through the u sub, let's see, I'm going to have an e to the u, and then the 1 over square root x dx, well that's a 2 du. Rip the 2 out front. I would rewrite 1 over e to the u as e to the negative u. Now it's easy to integrate. So that's a 2 times a negative 1 times e to the negative u. So this is negative 2 e to the negative u. Resubstitute, now I'm going to pull that right up here. I'm running out of room. So resubstitute square root x for u. And at the same time, I'm going to get rid of the negative exponent. So I'm write that as negative 2 over e to the square root x. So that's my antiderivative. I evaluate that from 1 to b. I shouldn't forget the limit as b goes to infinity. So we have the limit as b goes to infinity. See, that'd be a negative 2 over e to the square root b minus negative 2, so that's plus 2 over e to the square root 1. Square root 1's 1. So when b goes to infinity, that's 0. That's a constant. We get the limit to be 2 over e, which tells us that our improper integral converges. And since the improper integral converges, that tells us that our series converges. Thanks to the integral test. All right, the next one. You know what, let me grab the other piece of paper. See if I have a hint for you. The next one's number 27. When I look at it, the first thing that jumps out at me is, well, I know cosine of anything that's positive. Cosine of anything that's positive. I know it's definitely less than or equal to 1. So pause the video. Try number 27. When you're done with it, restart the video and I'll be here at the board working through it. Alright, number 27, we had the series n equals 1 to infinity, 3 plus a cosine 5n all over n cubed. So first off, my gut feeling on this, purely a gut feeling, is that it converges because the denominator is an n cubed. So let's see what I can do with that. You know, I look at the numerator, it's a 3 plus cosine 5n, and I know cosine 5n, the smallest it could ever be is negative 1, and the largest it could ever be is positive 1. That's kind of where I'm going to start. I know the cosine of 5n has to be less than or equal to 1. Cosine of anything is less than or equal to 1. Well, I can add 3 to both sides of this inequality. That's legal. And I can divide both sides of the inequality by n cubed. Okay, looks like I'm getting things set up where I may want to use the direct comparison test, where This is the a sub n, that's the b sub n. But I first have to determine that 4 over n cubed converges. And that's very easy for me to claim that it converges. First, we know the series 1 over n cubed converges. It's a p series. P is equal to 3, which is greater than 1. Because I know that, I know the series 4 over n cubed converges. Because quite simply, it is nothing more than 4 times the known convergent p series. So I've established that this converges. I've established that this inequality is true. I mean, I created the inequality, so I know that it is true. So I can now come over here and say, this series converges. Thanks to the direct comparison test with the series 4 over n cubed. We know that series converges. So that's it for number 27. I don't know, I find these kind of fun. Everything all thrown together. So, next up is number 49. Let me think of a hint for 49. When I look at number 49, I'm seeing rules of exponent can help me create a p series to compare to the original series. So that's my hint for 49. So pause the video, try number 49. Once you've done it, restart the video. You know I'll be here working through it. All right, number 49, you're asked, is the series n equals 1 to infinity, the 5th root of n over the 5th root of n to the 7th plus 1. Does that series converge or does it diverge? When I look at this, I'm kind of thinking, well, what if I look at the series, the 5th root of n over the 5th root of n over the 5th root of n to the 7th, just the 5th root of n to the 7th. So wait a minute, that series, 5th root of n over 5th root of n to the 7th, that's the same thing as the series n to the 1/5 over n to the 7/5, which a rule of exponents tells me this is the same thing as 1 over n to the 6/5, which I know this series converges. It's a p series. P is equal to 6/5, which is greater than 1, so I know it converges. So once I have this series that I know converges, I then think, is there a way I can compare this series to this series? In other words, can I satisfy the preamble of the direct comparison test? So remember, in order to use the power of the direct comparison test, my b sub n, my a sub n, if I know this converges, I know something that's smaller than it must converge. So I would need to have my original series, 5th root of n over the 5th root of n to the 7th plus 1. That's my a sub n. And so my b sub n is going to be the 1 over n to the 6/5, which is the exact same thing as this, which is the exact same thing as this. The 5th root of n over the 5th root of n to the 7th. Now, is this inequality true or is it false? The numerators are the same. This denominator is always going to be a little bit larger than this denominator. So I think this inequality is true thanks to our denominator argument. So our conclusion, the series n equals 1 to infinity, the fifth root of n over the fifth root of n to the 7th plus 1, it converges thanks to the direct comparison test with the series fifth root of n over the fifth root of n to the 7th. Ah, that one was fun. Alright, so next up, number 53. See, 53. Do I have a hint for 53? No. No, I'm not going to give you a hint on this one. Pause the video, try number 53. And after you've wrestled around with it, restart the video. I'll be here at the board working it out. We'll make sure you have the correct answer. Alright, 53. Does the series n equals 1 to infinity sine of 1 over n to the 9th? Does that converge or does it diverge? And I didn't give you a hint on this one. But I can tell you when I look at it, what jumps out to me is, you know, I'm going to compare this beastie to just the series 1 over n to the 9th. I mean, we know that series converges. It's a p series. P is equal to 9, which is greater than 1. So I know it definitely converges. I don't think I can crank through a direct comparison test. I don't think there's any way I can justify that sine of 1 over n to the 9th is less than or equal to 1 over n to the 9th. You know, I want to really look at using, because it looks a little messier, you know, rather than try to fight through the direct comparison test, and I could try to fight through it, I want to just practice using the limit comparison test. You know, so while I could come up with a way to do the direct comparison test, I want to review the limit comparison test. Because you remember the limit comparison test. Limit comparison test says you have to do the limit as n goes to infinity, a sub n over b sub n. So here that would be the limit as n goes to infinity, a sub n over b sub n. Wow, don't we have a mess here? You know, we have as n goes to infinity, this is heading closer and closer to 0. We know the sign of 0, 0. As n goes to infinity, this is 0, so we have 0 over 0, which is an indeterminate form, which should be screaming, let's go to the hospital. But you remember, this is my pet peeve. You can't take a function of n to the hospital. You can only take a function of x to the hospital. So no big deal. We come over here and we say, well, let's consider looking at the limit as x goes to infinity. Sine 1 over x to the 9th over 1 over x to the 9th. That's a function of the reals now. We can take a function of the reals to the hospital. See, the derivative of sine 1 over x to the 9th is cosine 1 over x to the 9th. Then we have to remember the chain rule. So we have to do the derivative of 1 over x to the 9th, which I get the derivative of 1 over x to the 9th to be a negative 9x to the negative 10th. Derivative of 1 over x to the 9th is negative 9x to the negative 10th. Neat thing happens, that cancels out. So we have the limit as x goes to infinity, cosine 1 over x to the 9th. As x heads to infinity, 1 over x to the 9th is heading to 0. We know the cosine of 0 is 1. So we can now claim this limit is 1. And since 1 is a positive finite number, I'm using the limit comparison test, we know, since this converges, I should probably write that here, it converges, it's a p-series. Since this converges, we know the series that we were given it too converges. And it converges thanks to the limit comparison test with the p-series 1 over n to the 9th. So there's a lot of good review embedded into this number 53. So let's see, next up, number 59. Let me give you a hint for number 59. In section 10.7, in the video I made for section 10.7, I did an example where that example can make 59 real quick in conjunction with the direct comparison test. So that's my hint for 59. So pause the video. Do number 59. After you've done 59, restart the video. I'll be here at the board cranking through it. Alright, here number 59. Does the series n equals 1 to infinity, n factorial over n to the n plus 3, does that converge or does it diverge? We see factorials, we see exponentials. We should be thinking, hey, good candidate for ratio test. But when I look at this one, I think, what about that series? Does that series converge or diverge? Well, in section 10.7, we did an example where we cranked this through the ratio test and we found that it converged thanks to the ratio test. We did that. We know that one converges. So now that I know that converges, I'm thinking, can I take this series and compare it to the series I was given? In fact, can I do a direct comparison test? Let me write down the preamble of the direct comparison test. This series would have to be in place of a sub n because we know that series converges. So the direct comparison test, remember it says if this converges, something that is smaller must also converge. Is this inequality true? And of course it is. We know it's true from the denominator argument. As long as the numerators are the same, and they are, this denominator is larger than that denominator, that means this inequality is true. So we immediately know that this series converges thanks to the direct comparison test with the known convergent series n factorial over n to the n. That's pretty slick. All right, so the final one, number 69. You know, when I look at this one, for some reason, I'm thinking E. That's my hint. So, pause the video, head off to the text, do number 69. When you're done, come on back, restart the video. I'll be here cranking through it. Hey folks, number 69, does the series n equals 1 to infinity, the quantity 1 plus 1 over 2n, all that raised to the nth power, does it converge or does it diverge? My gut feeling is immediately diverges. This is reminding me of, well, something that we know. We know the limit as n goes to infinity of 1 plus 1 over n to the n is equal to e. You know, in fact, we saw back in Calc 1 that in general, the limit as n goes to infinity of 1 plus k over n to the n power, that limit is e to the k. So when I look at this, when I see this, let me block this off. When I see this 1 plus 1 over 2n, all right, to the nth power, I'm really seeing this 1 over 2n as being the exact same thing as 1/2 over n. 1/2 over n is the same thing as 1 over 2n. So I immediately know that when I take the limit as n goes to infinity of 1 plus a 1 over 2n to the n, because this 1 over 2n is the same thing as 1/2 over n, I immediately know this limit is e to the 1/2 power, which is most definitely not equal to 0. Therefore, the series diverges thanks to the nth term test for divergence. All right, so that's a few of the homework problems. You should now be ready. You should crank through the homework in section 10.8, so you can do that now. And folks, this is all really, really important. Everything that we've done in chapter 10 is just a setup for what we're going to do next, which is called power series. And it's going to be very important that you know these tests and when they converge and diverge very quickly, because it's going to be just one small end piece of a typical power series problem. So go ahead, crank through the homework in section 10.8, and thanks for watching.